Hey mathematicians, here are your notes for 7.5, Graphing Systems of Inequalities. So throughout chapter 7, we have been working primarily on solving systems of equations, meaning more than one equation. But in 7.5, we're actually going to jump into inequalities. So we're going to take a little bit of knowledge from chapter 5 about graphing lines, and we're going to combine it with our chapter 6 inequality knowledge, put them together, and find our solutions for inequalities. Quick bell work though, let's go ahead and review this. What are the two things we need to remember after we graph an inequality? When and after. When we graph an inequality. So if you're like me, the first thing that you have to remember is that the sign changes the line. So if we had less than or greater than, that was just a simple dashed line. Whereas if we had the less than or equal to or greater than or equal to, that was a solid line. Much like this would be an open circle and this would be a closed circle on our graph. The second thing that we need to remember is that we shade our solution region. With a system of equations, there's really only one solution because that's where they connect, no solutions because they're parallel, or infinite solutions because they're the exact same line. But with inequalities, we're going to have to go a step further. So consider this. Let's get our brains warmed up with a word problem. Daisy wants to download songs and lectures on her smartphone. She plans to download at least 30 songs and lectures, but she can download at most 300 megabytes of data. So at least 30 songs and lectures, but at most 300 megabytes. If songs are 3 megabytes and lectures are 5 megabytes, what is the greatest number of lectures that Daisy can download while meeting both constraints? All right, I'm gonna give you a chance to try this one on your own, but first, let's identify some variables. Let's say that X is the number of songs and Y is the number of lectures. Using those, I want you to write two equations, one that talks about how many songs and lectures and one that talks about data limitations. Go ahead and try that one on your own. All right, hopefully I had time to give that one a shot. Let's go ahead and write some equations. The first one is going to be about how many songs and lectures. It says she wants to or she plans to download at least 30. So when I combine my songs and lectures, meaning when I add them together, the number when added together has to be at least 30, meaning greater than or equal to 30 pieces of information. However, it says she can download at most 300 megabytes of data. Now I know that songs are 3 megabytes and lectures are 5. So I'm going to have to multiply my number of songs times 3 to tell me how much data those are going to use. I then have to add the megabytes per lecture, which is 5 per lecture. And when I add those two numbers, my total megabytes have to be less or at most 300 megabytes. So it needs to be less than or equal to 300 megabytes of data. So how do I solve this? Well, these are inequalities, meaning they're going to have solution regions, not solution coordinates. Let's go ahead and look at shading and graphing these to get our solution that would answer our problem. While elimination and substitution can be useful for solving a system of equations because they only have one solution, one coordinate point, the best method for solving a system of inequalities is graphing. Why do you think graphing is the best method? Well, if I was going to answer this, I would say that graphing is the best method due to the fact that we have two solution regions, one per, two or more solution regions that must both must both be true. So let's find out if your conjecture or my conjecture is correct. So for this first one, I've got y is less than x plus 1 is y is less than or equal to negative 2x plus 3. Let's go ahead and graph these. So my first one, I'm going to do them in different colors. I think that sometimes helps. Remember that we're going to graph this the same way we would as if it was an equation. So I'm going to go up to 1, and then my slope is 1x, meaning 1 over 1, up 1 over 1, or down 1, back 1. The sign changes the line, so I check. I see that this is just a less than, meaning it is dashed. I'm going to go ahead and grab my straight edge here. I have misplaced my straight edge, but I have found it. I do like to be accurate when I make my lines. There is my dashed line, throw some arrows at each end, and then of course I check a point to see which side I'm going to shade on. So I'm going to check 0, 0, I plug it in. 0 is less than 0 plus 1, which is 1. That is a true statement, so I'm going to shade towards my point, going this way. Now, I don't like to shade right away, and you'll see why in just a minute. I like to draw those arrows to say I'm going to be going in that direction so that my picture doesn't get muddy. Let's go ahead and do our second one here, and we'll do it in green. So y is less than or equal to negative 2x plus 3. I go up to 3. However, my slope is negative 2, so down 2 over 1, down 2 over 1. The sign changes the line. I check. This is a solid line. Go ahead and make it nice and solid. Throw my arrows on the end, and I check a point. I love 0, 0. It's an amazing point. So 0 is less than or equal to, this would be negative 2x times 0, 0 plus 3. Is 0 less than or equal to 3? It is indeed, so I'm going to shade towards that point. And this is why I don't like to shade both regions. If I had shaded over here and now I shade over here, basically the whole picture is colored and I don't really know what my solution is. I like to go ahead and wait because now I can see where my arrows point together. My arrow over here points this way, but my arrow over here points away. So it's not this region. My arrow both here point away, so it's not this region. And this one points this way towards this, but this one doesn't point in. My last area is this one right here. Both arrows point together towards the center, so I'm going to go ahead and shade everywhere between those two lines. That is my solution region. So, is your conjecture correct? Is it true that two solution regions must both be true? Yeah, it is. And it's best if we only shade the one. All right, let's look at a second one. This one not as easy for some because it's not in that slope-intercept form we like, but we can still manage it even if it's not. I'm gonna bring in some new colors here. I'm gonna go ahead and do these in my standard form. So I'm gonna do 0, comma something, something, comma 0 to get my intercepts. When I plug in 0 for x, I get 0 plus y is greater than 1, y is 1. I get, when I plug in 0 for y, I get 0, 2x greater than 1. I solve, I get 1/2. It's okay that they're an inequality because even if they're not equal to these values, this is still where my line intersects the graph. So 0, comma 1, 1/2, comma 0. The sign changes the line. So this is a dashed line. This is going to be a third point there. It is going to be dashed. Dash that line. Throw some arrows on the end. And then let's check. Let's see what solution works. I'm going to check that 0, 0 because I love it so much. 0 times 2 plus 0 is greater than 1. When I check 0 greater than 1, that is not true. So I'm going to point away from that 0, 0. I'm going to point up, up, and away. One line done. Let's try the next. Same thing, it is in standard form, so I'm going to say 0, something, something, 0. And I'm just going to give you a second to see if you can identify those intercepts. Go ahead and try that. All right, so if we have 0 as our x, when we plug that in, we're going to, y is equal to -2. When I plug in 0 for y, I get 2x is less than -2. I get -1. That is our standard form solution. So 0, -2, -1, 0. And of course, the sign changes the line, so this is going to be dash. I'm going to pull it down here just so it's closer. All right. And then I'm going to check, of course. So plug in 0, 0. Do I shade up or do I shade down? In this case, when I plug in 0, 0 plus 0, 0 is less than -2. Hey, that is not true. 0 is greater than -2. So I'm going to shade this way. I'm going to shade away from that 0. But you're now asking, Miss Bury, they don't go together. Where do the arrows go together? They don't necessarily have to. They can go away from each other like this. And it's okay to shade where they're not converging. But then you ask Miss Bury, but then your conjecture doesn't make sense. Two solution regions that must both be true. How are they both true if they don't intersect? Well, those are still both perfectly good solution regions on their own. They don't have to be the same, and they don't even have to share any points because they're inequalities, not equations. All right, go ahead and try the next one on your own, and then come on back and we'll do it together. All right, let's give this one a try. I've been trying to pick out some fun different colors to do these in. I think that makes math a little bit more fun. So go ahead and do this first one, 2x minus 3 in a bright lime green. Go down to -3. My slope is up 2 over 1 or down 2 and back 1. The sign changes the line, meaning this one is solid. All right, don't forget those arrows on the end. I'm going to plug in my 0, 0. Love that point. 0 is greater than or equal to 0 minus 3. Is 0 greater than -3? It is. So I'm going to shade towards my origin, towards the point that I know works. All right, second equation. When I start, I'm going to go up here to +2, up 2 over 1 for my slope. And then the sign changes the line, meaning this one is also solid. Put those arrows on the end. And then check my origin. This way I'm going to shade towards my green line or away. 0 is less than or equal to 0 plus 2. 0 is less than 2, so I'm going to shade towards that origin. I draw my arrows to show where I'm going. And then I only shade in this case where they overlap because they don't face away from each other. So right in here is where both of them work. All right, and then the last one, you're like, Ms. Bury, that's got way too many things going on. Trust me, it doesn't. We got this. And I'm even gonna pull out some new colors here. Let's go these 3. Perfect. So let's start the first one. This one is not in slope intercept, so I'm going to go ahead and use my standard form 0, something, something, 0. And I plug 0 in for x. 2y greater than or equal to -2. Y is -1. Something, 0, and I plug 0 in for y. Ooh, that one's going to be a little bit gross. It's going to be -2/3. That's okay, we can still graph that. 0, -1, -2/3, 0, -2 up 3, that's where that one should go. Sign changes the line. This one's going to be solid. Looks like that. Ooh, my pen is running out. All right. Check that 0, 0. Do I shade towards my origin or away from my origin? 0, 0. Is 0 greater than -2? Greater than or equal to -2? Yeah, it is. So we're going to shade towards the origin, towards the point that works. Next up, x plus 2y is less than or equal to 2. This is another standard form, so I'm going to use that standard form method again. 0, comma something, something, comma 0. When I plug 0 in for x, I get 2y is less than or equal to 2. Divide both sides by 2, I get 1. Something, comma 0. Plug 0 in for y, I get x is less than or equal to 2. I'm just solving them as if they're equations. If you're having a problem with standard form and knowing where I'm getting these values from, you can go ahead and look back at note 6.5 or come chat with me. I'd love to work through these again so we're feeling confident in this unit. And then, of course, we shade. So 0, comma 1, 2, comma 0. Sign changes the line, meaning this one will be solid. I didn't grab a third point, but in this case, I can safely bet this is it. There's my blue, and then my green. Let's pull green in for the last one. This is a y greater than -1, meaning it's still just a horizontal line. Sign changes the line, meaning it is dashed. And greater than -1, if I plug 0 in, 0 is greater than -1, meaning I shade up. The only tricky problem with this type of problem is that now I have to figure out where all those arrows converge. So if we look at this one, let's look at each little individual region. Oh, I didn't draw my arrows for my blue one. Let's go ahead back and start that one. So if I check 0, 0 for my blue line, I'm going to get 0 plus 0 is less than 2, which is true. So I point my arrows down. It'd be nice to have all my arrows if I'm going to check this one. So I check my first region. I'm going to start down here. These arrows do point to each other, but unfortunately, this green arrow doesn't point down, meaning this one isn't it. Check my second region up here. Well, these two arrows point towards each other, but the blue arrow points down, so that's not going to work. They point away from this region. Blue and green converge over here. That's helpful, but purple points away from that. It doesn't point towards this, so that doesn't work either. This one, green and purple point away, even though blue points to it. So I've now tried every outside region, which means the only region where blue points in, purple points over, and green points up is this little triangle. And I could also have some fun and ask what the vertices of this triangle are, if I want to take it a step further. But I won't. If you want to, go ahead. This has been graphing systems of inequalities. Remember, the sign changes the line, we shade the solution region, and we always want to check those answers. So let me know if you have any questions.